Hi everyone, welcome to the video on stationary points. In this video I'm going to talk about the types of stationary points and how we can find them using differentiation. So to begin with, I've got just a few notes here. So three types of stationary points, and they are maximum, minimum and point of inflection. So these are seen in any of our polynomials with higher powers, but also in some of the other functions like trigonometric functions. The thing that all three of these have in common is that they all have a gradient of 0, so they all go flat at that particular point. As we can see with the maximum, it increases and then goes to a flat point where it turns and then it decreases. So it's that changing of gradient from positive to negative, and in between you've got that one point where it has a gradient of 0. So same with the minimum decreases to begin with, then it has a gradient of 0 where it's completely flat, and then it increases again. So again, the changing of gradient. Whereas a point of inflection, it increases, it has a flat section where the gradient is 0, and then it increases again. So in this case, the gradient is the same either side of it, in that it increases both sides or it decreases both sides, but it still has that moment or that point in the middle where it has a gradient of 0. So in terms of talking about the derivative, remember that the derivative is just talking about the gradient, and so if the gradient is 0, then that means that f dash x is equal to 0, or that dy dx is equal to 0, depending on the notation that you're using for the question. So let's have a quick look at a question. Find the coordinates of the stationary points of y equals 1/3 x cubed minus 7 on 2x squared plus 6x, and state their nature. So to begin with, what I'm going to do is I'm going to differentiate this, because I know that at stationary points the gradient must be 0. So I'll find out what dy dx is. Dy dx is, and now we'll take the 3 down the front, so 3 times 1/3 is just 1x, and then I decrease the power to 2, minus, I've got 7 on 2x squared, so I take the 2 down the front, it's going to cancel out with the other 2 here, so we'll be left with 7x, and the power should be 1. And then the 6x, when we differentiate that, that just becomes 6. So I found out what the derivative is. Next, I need to let the derivative equal 0. So I'm going to say let dy dx equal 0. This means that 0, is equal to x squared minus 7x plus 6. Now to solve something like this, we need to use the null factor law. And so I need to factorize this first. So I can say 0 equals, now I need to find two numbers that multiply to give positive 6 and add to give negative 7. So I think it's going to be x minus 6 and x minus 1. Negative 6 times negative 1 is positive 6, and negative 6 plus negative 1 is negative 7. And so the null factor law tells us that therefore x must equal 6 or x must equal 1. So I have these 2 points where the gradient is 0. And if I go back to the original function, y equals 1/3 x cubed minus 7 on 2x squared plus 6x, I can get an idea of what the graph of this might look like. And I'm only going to do it really roughly, ridiculously roughly by the looks of that. But it's a positive cubic. Okay, so the thing is, a positive cubic goes like that. Doesn't really matter where the points are or anything like that. I mean, all I need to know is the shape of it. This graph has a stationary point at x equals 6 and at x equals 1. So the 1 is going to be the point on the left, that stationary point, and the 6 is going to be the point on the right, that point there. And so I can find out what the coordinates of those points are. So I might just continue this over here. I can find out when x equals 1. So what I'm looking for here is the other part of the coordinates. I need the y value. And so I'm subbing it into the original equation. Y equals 1/3 of 1 cubed minus 7 on 2 of 1 squared plus 6 times 1. Alright, so then it's just a matter of evaluating that. Y equals, that's just going to be 1/3 minus 7 on 2, and then plus 6. Well, need to have a common denominator here, so I'm going to make it so it's all over 6. Y equals 2 on 6 minus, now I need to triple this, so I'm going to get 21 on 6 and then plus 36 on 6. So lastly, y equals, now what's that going to be? 36, so take away the 21, leaves 15, and then plus 2 is 17 on 6. And so this gives us the coordinates that we were after from the beginning. We know that x equals 1 and y equals 17 on 6. So that's the coordinates of the first stationary point. And remember that that was this point over on the left here. I also need to find out when x is equal to 6. So I'm just going to scroll down here. When, x equals 6. So y equals 1/3 of 6 cubed minus 7 on 2 times 6 squared plus 6 times 6. If I've remembered that equation correctly. Yep. Okay. This isn't so nice to evaluate by hand. So I've got 1/3 of 216 minus 7 halves of 36 plus 36. Well, what am I going to do here? So 1/3 of 216 should be 72. I've got, if I divide the 2 into the 36, so I've got 7 lots of 18. That's going to be 126. So minus 126. And then plus 36. So what does that leave us with? So I think if we work that out, it should end up being negative 18. And so again, this is giving us the coordinates of another point, which will be when x equals 6 and y equals negative 18. And so with all of that done, I've now got the two coordinates. I probably should make it obvious that that is part of my answer. And, well, it says to also state their nature. So, as I was saying, the point that's on the left, the smaller x value, is a maximum. We can see this because of the shape of the graph. And that the point on the right here is going to be a minimum. So that was when x equals 6. And so this one here, we can say is a minimum. This one up here we can say is a maximum. And again, it's just referring back to the general shape of the graph. There is a little bit of language around this. In this topic, we can talk about local minimums, local maximums, absolute minimums, absolute maximums, and then another name for them is a global max or min. So what I'm going to do is, just off on the side, I'm going to draw a bit of a graph. That wasn't ideal. That's a bit better. So if I have a look at something like this, I'll put some endpoints on it. When I talk about the types of minimums or maximums, you can see that I have minimum here, and I've got a maximum here, and I've got a minimum here. So in this example, this point right here would be called an absolute or global minimum. And this point here would be called a local minimum. So the difference between them being that this point here is the lowest point that the graph actually reaches, whereas this point over here is just it's a minimum, but it's not the minimum value of the graph. And so while this here is a local maximum because it's a maximum but it's not the highest point that the graph reaches, what I can see is that this point up here is the highest point of the graph, and so I would say that is the absolute or global maximum for this graph. Okay, and so when we're describing the type of these, we only really need to say whether they are maximum or minimum, but yeah, this is just a bit of language around it, which I think is handy to know about. Anyway, I'm going to leave that video there, and yeah, see you all next time.